All right, good morning. You guys ready for Thanksgiving?
Yes.
So I've not yet posted your last homework, but I will this afternoon. So you'll have that. You're welcome to ignore it till after Thanksgiving. You have my full permission, but I'm also wanting to make sure you have it there before, in case you did want to spend some time on that. Okay, so today then my aim is to finish off with the BOD measurements. There's a chance I don't get quite all the way through it. I think I will, um, and if not, then that's probably like the last part of the last problem on the homework. Something like that will be. You could look ahead in the book or in the notes. Probably figure it out, or you could wait till Tuesday after Thanksgiving. But here we are. This is where we came to last time, talking about measuring the 5-day biological oxygen demand of a sample, and we were talking about how with a typical sample we're going to have to dilute it because usually we're investigating water that's going to be a problem when you add it to other water, right? So the point is it's going to drain the oxygen in in whatever amount we have it. If we discharge wastewater straight into a river, that's diluting it, but the net is going to drain it of oxygen. So typically, anytime we're measuring some BOD, we already kind of know in the first place that it's going to be strong enough to just remove all the oxygen, and then you just can't measure anymore. So that's sort of the point of setting it up in this manner, expecting we have to dilute. So we covered the dilution factor, defined all these terms nicely, and essentially, in the simple sense, it's very straightforward. You measure before and after, divide by the dilution factor or the ratio of um, wastewater to total water. Right. So then, just a real quick problem here, then can get us going and thinking about it in that manner. We have a 10 milliliter sample of sewage mixed with enough water to fill a 300 milliliter bottle, and that has an initial dissolved oxygen of 9 milligrams per liter. To help ensure an accurate test, it is desirable to have at least 2 milligrams per liter drop in dissolved oxygen, so going from 9 down enough at least to 7, right? So two points down during the 5-day run, and the final DO should be at least 2 milligrams per liter remaining. So then, for what range of BOD5 would this dilution produce the desired results? Okay, so I'll just put up our equation here. So you kind of see the way I set it up here. The range, for what range of BOD5 would we have a kind of a valid answer, with BOD5 equation being initial minus final divided by the dilution factor. I could go ahead and solve for the dilution factor. Because we were given 10 milliliters of the sample, 300 milliliters total, that's a ratio of 1 to 30, or 10 to 300. And so I kind of set it up with those two knowns, plus the fact that our initial DO is 9 milligrams per liter either way, right? So then the question really is asking, well, what do we need to put in for the DO final for these two cases? And if we think about that, the minimum, we had to drop at least 2 milligrams per liter. And so we can just actually put in that 2 here. So it has to drop at least 2, because that's going to be the change that we're confident we can measure with this oxygen probe. Hopefully we had a better accuracy with our probe, but we can, if that's what we're working with, that'll give us some answer there, which should be 7 on top, essentially times 30. So that should be what, 210? 210 milligrams per liter there for that one. So at least that. I'm sorry, I did that all backwards. That's the max, right? So you guys are giving me funny looks. Yeah, the final has to be at least 2 less, right? So that should be 2 there, which means this is 60. Is that better? So what I was saying a moment ago, I put if we had to keep at least 2 at the end, right? So then for the max case, we could drop all the way down until we had 2 remaining. So that would be the max BOD removed before we're no longer trusting our test. And here's that 7 times 30 to give us 210 milligrams per liter BOD. And to be precise, I suppose we could say BOD 5. I'll probably not always write that out. And if I don't, then we can assume it's BOD 5. We could technically solve something for BOD 4 or 10 or something, right? But convention is BOD 5. All right, does that make sense? Okay, so with high strength wastewater, we saw in that previous example, we did a 30-fold dilution, meaning it was a 1 part wastewater for 30 parts total. That's a pretty significant dilution, and that can only get us to 210 milligrams per liter BOD, right? So if we do really high strength wastewater, 500 milligrams per liter, something like that, we're really talking about quite a big dilution. And what that means is our dilution is so strong that we're probably going to be creating a situation where we don't have enough bacteria to perform this BOD in the 5 days, right? We would probably take several days before the bacteria colonies that do exist from the little bit of wastewater we add to cover the whole system and to reach a high enough number to consume it as if we discharge this into nature, right? Natural waters tend to have a lot. If we're diluting with pure lab water, that's actually not conducive for an accurate BOD test. So what we do then is add a bacterial seed to our dilution so that our dilution is not so dilute in terms of bacteria count. But doing so is inevitably going to add a bit of BOD itself, because when we add bacteria, usually we've generated the bacteria, given them stuff to eat, and some of the bacteria will die and there'll be dead cells and things. So inevitably, when we add this dilution volume, the dilution itself is, when we seed it, is going to have some BOD. So now we need to distinguish that. And it's just a bit of algebra, but we're going to go through it to make sure that we can see it all clearly and understand what we're doing with this type of problem, to get a careful analysis. So as an example here, what I'll say is, if we have a full bottle filled to the top, and we have a bit of wastewater at the bottom, a tiny bit that we add there. Then we have a bunch of volume for dilution. Then essentially what we're going to add in addition to that would be this seed. And essentially we're going to consider it just as part of the dilution water. So really, I guess we would fill that up and say this is all volume of dilution. But I'm just writing it that way to kind of show you we're seeding it. And so this all comes together in that manner. Okay. So our equation then, when we have BOD in the actual dilution, if we want an equation for the BOD5 of the wastewater, we have to consider it in the context of the BOD that we're actually measuring. So this equation here is showing us, well, when we make an observation for this total volume, what we're looking at is essentially the BOD in the volume of the wastewater here. So this is actually just like any of our mass balances where we say concentration times volume is giving us the mass, right? So the milligrams BOD per liter times the volume is going to give us the BOD of wastewater in this particular vessel, right? And so we'll do the same thing for the VD, milligrams BOD coming from the seed per liter times the volume. Gives us the net total. So right, that's what this equation up here is telling us. We have the total BOD in the volume is equal to the BOD from the wastewater plus the BOD in the dilution water. Okay, so very straightforward there, but I just want to be kind of elaborate to show you we're going to take this equation and solve for BOD of the wastewater because that's ultimately what we want to know, right? We can observe with our experiment this guy. And in the context of all of these things, and usually we'll know something about this or we'll do it on the side. So we can say this is known, or I'll say measured simultaneous, because we can set aside a bottle of just dilution water with the seed. It should have plenty of bacteria because it's got the seed in it. It's got a little bit of BOD. It's not going to really need dilution because it should not have that much BOD in it. And so that we can just set on the side and measure at the same time. But, okay, we now know this. This is what we want to know. That's what we're solving for, and this is measured. Okay. And of course, we know the volumes that we put in each. Okay, so in this case then, this equation, we're talking about this BOD5M, that's the mixture. So if M is the mixture, D is dilution. Really all we're saying is that, again, the P is the volume, the wastewater divided by volume, the total volume. 1 minus P, however, by the way, so some algebra that we'll use when we solve for this. 1 minus P is going to be VD divided by VM. We could get that with some, algebraically from that. I'm just going to leave it right here as part of kind of how the book takes us. This will become relevant in a moment as we see how the book derives a better equation, or essentially the equation for BOD wastewater equals what, right? So that's what we're aiming at. It's getting an equation here. And of course, we could just take that and aim towards that, derive that ourselves algebraically. I think it'll be a little more convenient to just put up what the book does and kind of walk us through that. Okay, so to do so, the first thing we can do is divide everything by the volume of wastewater. That gets BOD wastewater by itself. So if we divide everything by volume of wastewater, then over here we've got VD over volume of the wastewater. That's what I was talking about a moment ago when I said the VD over the mixture, that parameter might be useful. So this is pretty close to that. Clean that up. And we're also going to divide this by the volume of the wastewater. Okay, so that puts us here. We also go ahead and subtract BOD, the dilution from both sides. So BOD, the wastewater, is going to be the BOD of the mixture times the volume of the mixture divided by the volume of the wastewater minus the BOD of the dilution water times dilution volume divided by the wastewater volume. We can simplify further with that whole 1 minus P business, or 1 over P rather, or 1 minus P and 1 over P, right? So right here, volume of the mixture divided by the volume of the wastewater is literally the inverse of P. So that's 1 over P. And then we subtract from that what was remaining over here. It's the BOD of the dilution times volume of dilution over the volume of wastewater. And here's where they insert a little bit of that algebra to get to here. I think they're just doing that simply to put everything in terms of P. Now, obviously, we need the volume of dilution and the volume of the wastewater to know P, so it's kind of moot, and I almost feel like it would be simpler to leave it as it was, but that's what the book wants to do, so we're just going to believe them that volume of dilution divided by volume of the wastewater is equal to 1 minus P divided by P. Okay, and if you wanted to, we could sort that out and prove that algebraically. All right, so that gives us an equation. All told, and this is probably why they decided to stick with just P, because it does simplify nicely. The 1 over P is here and here. So all told, we have BOD of the wastewater is equal to the BOD of the mixture minus the BOD of the dilution, and that dilution times 1 minus P. So 1 minus P, by the way, conceptually, it's like 1 minus the fraction that is the wastewater. So this is the fraction that is the dilution water, right? So, and actually you can see that just right from here. It's very plain to see there. If P is the fraction that is wastewater, 1 minus P is fraction that is dilution. Okay, so we've got this equation then, and this is for seeded dilution water. You can recognize that if we had a situation where there was no BOD in the seed water, this goes to 0, and we're left with the BOD of the mixture divided by P, which is DO initial minus DO final divided by P, right? Just goes back to the equation we started with. Okay, so this is for the case where we have dilution water that has BOD in it. If you decide to just use this equation all the time, just recognize sometimes that'll be 0 if you didn't need seeded dilution water. All right. So all that said, I mentioned this earlier, but if we fill 2 bottles of water, so we'll typically do this with 2 measurements. One where we have straight up volume of dilution the whole way, and the other where we have some volume of dilution and some volume of wastewater. Go ahead and get brighter color for that. Okay, so with that, then we'll do two experiments at the same time so that we can know the BOD of the dilution will be coming from this, and we'll get the BOD of the mixture from this. So just stepping backwards a moment, in order to solve for the wastewater, we need the BOD of the mixture and the dilution. So these are those two experiments, right? So we'll have two bottles. And the way we're going to phrase this is we're going to say for the mixture, this portion of it, that's going to be the DO initial. So DOI is initial. Dissolved oxygen, as we talked about earlier, DO final. It's the final for this guy. And then just to avoid confusion, our equation here is going to use a separate letter to mean dissolved oxygen in the other bottle. Okay, and that's going to be B. So BI is initial DO. Whereas B final, or excuse me, BF is the final dissolved oxygen. Okay. These are for the dilution bottle. All right, does that make sense? Okay, so a quick problem then. Here we have a test bottle containing just seed dilution water. It has a DO level drop of 1 milligram per liter in a 5-day test. A 300 milliliter BOD bottle is filled with 15 milliliters of waste, so this would be a separate bottle here. A 15 milliliters of waste, and the rest is that seeded dilution water. Gives us that P of 1 to 20. And that one experiences a drop of 7.2 milligrams per liter in the same period. What would be the 5-day BOD of the waste? So take a couple minutes and solve that, and notice that the way it's phrased is a little different. You know, we're just talking about the BOD drop. So give yourselves a few minutes to think about how that one works through. so we've got a p-value here, 1 and 20, should be 0.05. 1 minus p then would be 0.95. So the 7.2 milligram per liter drop for the mixture here, what that'll kind of show us is that we started with some amount and dropped 7.2 milligrams of, I wrote BOD, I probably should just say oxygen here. We are treating that as if it's oxygen, right? I said BOD, but that's kind of the point of the test. So technically, I guess the more correct thing to say would be that's oxygen that we measured. This is oxygen that we measured. Milligrams of oxygen per liter. When we talk about it in BOD, that's then the contents, right? But kind of doesn't really matter. Okay, so anyway, the dilution itself had 1 milligram per liter of oxygen drop. So that's just 1 here, 7.2 minus 1. But that 1 is times 0.95. So that's going to be 7.2 minus 1 times 0.95. All of that then divided by 0.05. So we can take essentially 7.2, and 1 times 0.95 is just going to be 0.95. So 7.2 minus 0.95, 0.625, and then to divide by p, we can just multiply by 20, right? Just carry that up. So we can take this and multiply that by 20. And so our BOD in this case is 125 for the solution. Okay. Does that make sense? Let's get that. All right. Okay, so with that, the next target is to really get a good way of understanding what's happening downstream. We want to know if we discharge some wastewater that we've treated or not treated or whatever, what's the impact downstream and how far away is that impact going to be seen? And ultimately, the highest priority is to predict the worst case scenario. At what point does the dissolved oxygen in this river, let's say, does it reach the lowest? And have we treated our wastewater sufficiently so that that lowest number has no meaningful impact on the ecology, right? Because that would be a good design. So if let's say we've disinfected our wastewater and we've cleaned up any toxic stuff, so this conventional pollutant, the BOD, could still be a problem just by causing oxygen demand, right? If we dumped a bunch of sugar, right? It doesn't sound like that's too bad of a thing, but if that causes this oxygen demand, we're going to harm the environment in a meaningful way. So what we want then is to control our system so that, yes, we know that we're going to cause some oxygen demand in the river, but if the aeration is happening quick enough, just by the natural gas transfer and all of that, hopefully it's not even going to be a problem. Maybe some of the fish will prefer swimming to a different spot, but ideally it wouldn't even get to that point. So the deal here is then, if we think about a river flowing, wherever it's going, we can consider the time and the distance to be fairly similar in terms of where we started with some sort of discharge, perhaps, and as it flows through, it's often going to be a lot like a plug flow reactor. So we're specifically going to look at rivers, streams and rivers here. Lakes would be similar, but the math's going to be a little different. And so really what we're looking at is downstream here. So we can consider time is effectively distance downstream, so long as we know the velocity that the current is flowing at. Okay, so if we take a plot of the dissolved oxygen and the time or distance since a discharge, so let's say we have a wastewater outfall here, we've got a continuous discharge, and we're tracking what's happening downstream. 5 minutes downstream might be, 100 yards to 200 yards downstream. We can check it. And essentially, if we have a dissolved oxygen kind of maximum, the saturation point, we can use that as a reference point. Most river waters are not actually going to be at saturation. Sometimes our wastewater will be if we've just been oxygenating it right before discharge to make sure that it's got the water itself is not lacking oxygen. And so typically a river water is going to already be slightly below saturation, just natural biological activity. So we'll probably start slightly below, and then as the biological activity begins to consume oxygen in the river water, we've got a condition where we will have a sag curve, and at some point it's restored back towards sort of its natural state, towards the DO saturation. If there was no extra organic matter ever added to the river at all, we might end up reaching saturation or something like that. But essentially what we have going on is two rates. We have a rate of O2, we could call it re-aeration. I think I spelled that wrong. And then we have O2 demand. And these will be competing and participating the whole way through. And as we'll see in a couple slides, we've got the rate of re-aeration actually depends on how much dissolved oxygen deficit we have. So the more we lack, the more oxygen wants to get into the water from the atmosphere, which is quite helpful. Okay, so then a couple of things here we can describe. Of course, DO, again, is dissolved oxygen. So what we plotted here is different dissolved oxygen points, DO at some time t or distance x or something, right? So we could just say any dot along that line is what happens to be the DO at that particular time. Then we could also take a look at the deficit at that particular point. This is completely arbitrary. I'm just drawing up a random point here. And so we could say that oxygen deficit, OD, and I actually think that later we're going to just use D for deficit. I don't think we normally keep the O there. So D would be the O2 deficit. So what we're describing here then is how much oxygen is lacking from the water compared to what would be if it was saturated, given its temperature, given the particulars of the environment, right? Okay, so those are two concepts that will be very important. Of course, dealing with this equation and how to make this model, it's a lot like a plug flow reactor. Okay, we're going to be taking the water, sending it through this process. It's got competing reactions and several factors that can describe how and why we have the increase or the decrease. We've talked about the BOD from kind of that culturing standpoint in terms of how much substrate there is, how much bacteria there are. We're also going to add to this the re-aeration rate. And we're not going to be doing too much of the solving of the mass balances here, so much as kind of understanding how they're working together and then applying some equations accordingly. Okay, so as we consider how to find, how to understand this dissolved oxygen, and perhaps the big question here is when and where does this, the most extreme deficit occur? Oops. one of the useful tools we can use from a kind of a experimental laboratory type of approach would be the total organic carbon, TOC measurements. TOC is a common instrument. We have one in our environmental shared lab. It's essentially going to do pretty much what the chemical oxygen demand type of system does, in that it's going to cause whatever's in your sample of water to combust, if at all possible. So we're going to put it under very harsh oxidizing conditions and then measure how much carbon comes out of it. First, you have to purge the CO2 and all that, but essentially what this is going to give us is, as the method says, the total organic carbon, or an estimation of it. So you could also track total organic carbon as a function of time or distance from your discharge. And in this case, assuming that we're not adding significant amounts of organic matter from other sources, other wastewater discharges or whatever, at least in terms of the human impact here, what we would see is the TOC should be decreasing over time. Something like that, right? And that should probably be first order. And so unless we linearize it, it's going to have that nice kind of exponential decay type of a look. That would be a decent estimation of the substrate concentration that we talked about in the context of wastewater, right? So that amount of substrate that didn't get treated, that was discharged out, then the biological processes are taking care of it. And this would also apply if we were to consider like artificial wetlands, things like that. How are they processing the organics? Well, there's going to inevitably be a process that's consuming or taking care of that biological demanding substrate. Okay, so the DO sag curve then is essentially, mentioned already, like a plug flow reactor. And what we're going to do is sort of model the two. Kind of was ahead of myself and already described all of this. So I'm just going to pretty much skip it. But it's a mass balance on BOD, right? Or really mass balance on oxygen using BOD. So oxygen demand from the biological activity compared to the physical reaeration, right? So we have got that physical process reaeration versus the biological O2 demand. Okay. And if we put that in a plug flow reactor, that time is essentially distance. Okay, so how quickly is BOD removed? Well, we didn't quite derive the equations for that during our wastewater conversation, so we're going to get into that a little more here. So if we define this term L with some subscript as the amount of BOD remaining, so not the amount that has been consumed already, but the amount remaining at some time t. So L naught is then the BOD remaining at time 0. If we define it in that way, this is different than saying the BOD 5. Okay, so this is a little bit tricky because what we're talking about here with L naught, that's the ultimate BOD. That's BOD infinite is L naught, right? So L naught is equal to BOD if we could measure for an infinite amount of time. That's the oxygen demand remaining in total. Okay, so since we're talking about a river water here, we're not talking about BOD 5 remaining necessarily, although we are usually going to measure it in BOD 5. If we do a measurement, it's going to be BOD 5. But in theory, there's more than what can be consumed in 5 days. Okay, I said already we could do 3 days, we could do 10 days. We'll get different values, but 5 is the standard. So that's my point here, is this BOD remaining then at some time t, maybe it's 6 days in, so we've already passed what the BOD 5 value would have been, but there's still some remaining. Okay, this is understandably can be a little bit confusing because we haven't talked about it in that reference yet, but this lets us say, well, the total remaining changes with time. Okay, that lets us have a kind of a rate analysis approach where we say dLt dt is equal to negative KLT. So this would give us a BOD reaction rate constant, the rate at which it's being degraded over time. First order decay, so LT equals L naught times e to the minus KT. And last thing I'll say about L naught is this is the L naught for a river typically after the waste has been added. So if we have a wastewater outfall, rivers flowing this way, we take right after that, we'll say this is what we're talking about, the BOD of the river plus the BOD of the wastewater. So those two combined would be L naught. All right. So one last thing here. So that's just a kind of a side note. One other thing about L naught, we have another equation here, and that is that the amount of BOD, the BOD ultimate at any time is going to be the BOD that we measured after that amount of time plus the amount that's still remaining after that measurement. Okay, so if we take L naught and say it's the ultimate amount in this river is 100 milligrams per liter of BOD. Well, if we measure after 5 days and the 5-day measurement gave us 70, then the amount remaining is 30. Okay, so if L naught equals 100, and a BOD 5 measurement was 70, L at 5, so the amount remaining after 5 days is 30. Okay. We would still call that milligrams per liter of BOD in that case. All right. So hopefully that makes some sense. This is it is pretty straightforward so long as you recognize that we're deviating from keeping to just the 5-day format necessarily. Okay, so that's our equation for BOD consumption, or so oxygen consumption, so the oxygen demand portion of our equation. So now we're going to look at deoxygenation. To wrap that up, forgot I had a little bit. So to wrap up the deoxygenation portion, we could say KD is a deoxygenation rate constant. If we're going to define that rate of deoxygenation, it's going to be directly related to the BOD consumption, right? So we'll say the rate of deoxygenation is going to be equal to KD, so it's this rate constant, times the ultimate BOD times e to the minus KD t. So that's just an equation that we have. If we look back for a second, we have an equation for the BOD removal, but that's going to be distinct from the oxygen demand itself. Okay, they're related. This is the term that relates them. So we'll use this term. Typically, we'll have KD as a known provided given a particular water condition. Okay, so we've got this equation for the deoxygenation. We'll be able to solve for something about L naught if we have to, or maybe that's known. Okay, so that's all the deaeration, or the, I guess, deoxygenation there. So reaeration then is a physical process. It's proportional to how much oxygen there is at saturation compared to how much there actually is at the current value. And that's where we'll define the oxygen deficit, or D here. Apologize for the slides being slightly wrong earlier. So the reaeration rate then would be a growth rate of oxygen depending on some rate constant and depending on the deficit, which is really kind of strange, right? We're going to have a rate that's dependent on a deficit. So it's going to be an awkward rate equation in that sense if we were to define it in terms of DO directly. Defining it as deficit is going to be actually kind of nice because it's just K times D. So the KR, this is going to be, again, a first order per time units for the K. Deficit, again, is at saturation minus the current. And it turns out that the K, this KR, K for reaeration, people have empirically defined typical values, or have even looked at enough streams and rivers to say, well, there's a few ways to derive it. This is one that the book suggests is a good one. And we're going to say that if we measure the speed of the river and we know the depth of the river, then we pretty much know enough to know this rate constant for the reaeration. So this is going to be, and this is not theoretical, this is empirical, meaning they just measured it in a lot of rivers. Okay, so that's just the how they derive this equation. And it typically is 3.9 times the speed to the 1/2 power divided by the depth, or the height, I guess, to the 3/2 power. Okay, so that's just what they found to be generally true. So I'll give you that. And then if we had some information about the river itself, we could calculate this, right? And so basically what this is saying is, if it's running really fast, it's getting a lot of mixture, a lot of contact with the air. You can imagine a waterfall is going to be a lot of reaeration compared to a slow-moving bayou, right? And the depth is also going to matter. Even though the Mississippi moves pretty quickly, it's also quite deep, so we can imagine a lot of that water is not getting contact with the surface, with the atmosphere. So there's going to be some limitations to the reaeration at a given point in the Mississippi. Okay, so also kind of explains why in Louisiana especially, you'll see a lot of ponds with fountains, right? Just vastly improve that reaeration for the pond so it doesn't get so stagnant, so that it has plenty of reaeration. Makes for a nicer environment for fish, wildlife, and people. Okay, so a few typical numbers here. We could use these or select, I guess, something in these ranges if we wanted to. For the reaeration constants, just to give you a picture of it, small ponds, backwaters, 0.1 to 0.23 per day would be typical numbers here. This is at 20 degrees Celsius. We've got sluggish lakes, 0.2 to 0.3. Large streams of low velocity, 0.3 to 0.4 for almost 5. Large streams with normal velocity, 0.46 to 0.69. Swift streams, 0.69 to 1.15. Rapids and waterfalls, more than that. Okay, so that's just kind of an example there to make that a little more clear. Okay, so if we take a look at the rates, if we were to plot the two rates, the reaeration and the deoxygenation, on the same graph, what we can see is the rate of deoxygenation based on the BOD consumption is going to be high at first because we have a lot of BOD remaining. So LT is high here. But once there's almost no BOD remaining, where LT is nearly zero, they have nothing else consuming the oxygen, right? So that has decreased substantially by this point. So then the rate of reaeration is pretty low at first because the oxygen itself is high. We start off with pretty close to saturation. And you see this is starting at a non-zero because we're assuming we're not quite at saturation at the start. Because the rate of reaeration would actually be zero at time zero if it was at saturation at time zero. Okay. But if we let this river or stream run for an infinite amount of time with adding no organics at all, LT eventually gets to zero. That means the rate of reaeration, once it pulls that oxygen back up towards saturation, well, maybe eventually we get to saturation and then the rate of reaeration would get to zero. But you see here, it's still remaining slightly above it. Okay. So, my computer wants to restart and force me into Windows 11. Not right now, please. Okay, so then if we take a look at the dissolved oxygen in the system, again, we said we were not starting at saturation. We start maybe here. We have some sag. We reach a critical point. That's ultimately what we're interested in finding before going up. So this the top graph corresponds to this one here. So that's the other thing you'll notice is this this critical point here, this XC or TC, that corresponds to the highest rate of reaeration because that's the highest deficit we found. Okay, so when we take a look at the math for these situations, that kind of worst case scenario, the highest deficit is also the highest reaeration moment. Okay, so then let's talk about the mass balances and the equations here. So if we're going to derive an equation for the deficit over time, we could say the initial deficit is D naught. Deficit at some time t is, we'll just leave it as D. So the dd dt is going to be the deoxygenation rate minus the reaeration rate. And so that would look like this portion, which we talked about, that's the deoxygenation, depends on the ultimate BOD there, minus that Kr times D, that was the deficit, right? So this is straight from where we just were. That will give us a combined rate equation, like the net stuff that happens to the deficit. Turns out it's a little bit easier to look at the deficit than it is to look at the straight up dissolved oxygen. So now all we have to do is integrate that. All right, go for it. Kidding. Okay, so we'll let the book do that for us. So the integration there, if we assume the book is correct here, is Kd times L naught divided by Kr minus Kd. All that times e to the minus kdt minus e to the minus krt, and then plus d naught times e to the minus krt. Okay, so that gives us a deficit at some time t, given the parameters that go into these two rates, right? It'll be the kr, kd, that'll be the time, and it'll be the ultimate BOD in the solution. It's pretty handy, all things told, unless we accidentally get a condition where the reaeration rate constant happens to be equal to the deoxygenation rate constant, because then this goes to a zero on the denominator. So we have to have a special case for when that happens. this is not the rates of reaeration and deoxygenation. That is the rate constants, right? So that's just if we find in the situation they happen to be the same value, we have a problem. So we'll have a second equation, but this is going to be the normal equation under normal circumstances. And that'll give us a way to understand how much deficit we have at any given point. But we still want to know essentially what the maximum deficit is. So Dmax is still sort of a question that we'll come back to in a moment. So if we have that problem where Kr happens to equal Kd, we're dividing by 0. So if and only if we have that case, we have a second equation from the book that says, well, a simpler estimation, then we can say deficit is equal to Kd times L naught times T plus D naught times e to the minus K dt. Okay. So we'll give you that one as well on the formula sheet, but that's should only be used when Kr happens to be equal to Kd. Okay, so that's all well and good, but when does that happen? That remains the question here. When do we get that deficit? And so that's going to be the challenge here is to find that time of the critical point. And if we find the time, we'll know the distance, right? So we can then target our perhaps field assessment efforts to a particular location, given that we know it should happen 3.5 days after the discharge. Okay, so TC then is that critical point, or the time elapsed between discharge and XC, if XC is our critical distance there. So TC then is equal to, and this is coming from kind of some derivation from the previous equation we looked at. Again, note that we can't really deal with it properly if we have that dividing by a 0. So we really, I guess we have to only be doing this with this equation here. We might be able to find it from here, but I don't think the book gave us that, so we're not going to bother. So here's the equation. TC is 1 over Kr minus Kd. That quantity times the natural log of Kr over Kd times 1 minus D naught times Kr minus Kd divided by Kd times L naught. All right, so big fancy equation there. All the parameters. Again, really what we're dealing with is the rate constants, the initial deficit, and the ultimate BOD. Okay, if we know those things, we can put in all the numbers and get our time. And of course, you know from simple physics that our distance is going to be the velocity times time, and that the time you could solve by taking the distance divided by the velocity. So using that, and assuming that the river velocity is constant, of course, if we have inputs from other streams and natural occurrences like that, it will become more complicated. But with these assumptions, we can get that time critical, and it turns out it's a pretty good metric to use in order to understand the impact for wastewater discharge. All right, so my goal in all of this is to help you see how the types of things we've been learning can apply here, even if we're not deriving all these ourselves. We can see how it's coming into play and have an appreciation. And using some equation like this, we could do it ourselves in terms of solving those problems. All right, so I'll read through this problem for you and maybe make a couple comments. I'm not going to spend the time to solve it with you this time. Maybe we'll do that after the break. So I'll read through it. and let you go. So here's an example for dealing with something like that. The wastewater in a previous example has a dissolved oxygen of 2 milligrams per liter, discharge rate of 1.1 cubic meters per second. The river's receiving this waste has a DO equal to 8.3, a flow rate of 8.7, temperature 20 degrees. Assuming complete and instant mixing, we need to estimate the initial dissolved oxygen deficit of the mixture of the water and wastewater just downstream. Okay, so that was just saying, okay, what is the essentially L naught, right? This is the, in order to get L naught is one of the questions, but this is actually asking for the initial dissolved oxygen deficit. So this is really essentially two streams meeting, each with their own deficit. So deficit for the river, deficit for the wastewater gives us a D naught given some flows, right? So that part is very simple. And then we can go on with a second example. It says just below that, essentially we have some specific BOD, river conditions there, gives us some of them. And here we're asked to find the maximum distance. So that's looking for the TC. And then find the minimum value of DO. So that's deficit is DO at saturation minus DO at time t. Okay, so a couple examples there if you'd like to work through them, but I'm just going to let you off there. Say happy Thanksgiving, and I'll get a homework posted for you soon.